Okay, so for today, we're going to go back. So we have finished off on Tuesday, week 12. We look at Mohs criteria. So this is Mohs criteria that I've drawn. So anything that is bounded within the boundaries, it means that the structure will not yield. Anywhere outside, the structure will yield. Okay, so we have derived an expression to state that stress A, the principal stress A, right, divided by the ultimate tensile strength minus by the principal stress B divided by ultimate compression strength, and this will be equal to 1, where stress A and stress B are principal stress. Okay, they are our principal stresses. So like what I mentioned before or last week, just to quickly recap, where stress A over stress ultimate tensile minus by stress B over stress ultimate compression. If this entire term is less than 1, right, the structure will not fail. Or will not yield. It's not failure, it's yielding, okay? It will not yield. Okay, so we just look at an example. If our ultimate tensile is equal to 1, okay, and our ultimate compression is equal to 5, okay, so it's equal to 5, right? And then now let's say let's look at condition number 1. So you can see down here condition number 1. So I'm going to put in arbitrary number. So condition number 1, right, where you have stress A is positive, so stress A over here is equal to 0.2, right? And then stress B, okay, stress B, we put a value of 1.5, for example, okay? So that is condition number 1. So when we substitute everything in, okay, so we have 0.2. So you have to put minus, okay? Stress B is in compression. So stress A is equal to 0.2. Divide by ultimate tensile is 1, right? Then the whole thing minus by stress B. So this is bracket minus 1.5. Then divide by ultimate compression, which is equal to 5. So this will be equal to, so 0.2 divided by 1 is 0.2, right? Minus will be plus 1.5 divided by 5 is equal to 0.3. So this will in fact is equal to 0.5. So 0.5 is over here is less than 1. Okay, so the structure will not yield. Okay, and then if we look at condition, the next condition, so if stress A over stress ultimate tensile minus by stress B over stress ultimate compression, right? And over here, if this whole thing is greater than 1, the structure will yield. Okay, so another example, if we look at condition number 2, and condition number 2 is over here now, so it's outside the operating bracket, as you can see. So we have condition number 2. All right, so I'm going to write down condition number 2. Where stress A is equal to 0.2, right? And then stress B is equal to -3, for example, okay, -3. Sorry, in fact, it's not over there, okay? So condition number 2 is somewhere down here. I do apologize. Okay, so condition 2. So A value is still the same. Now we are outside over here. and this is condition number 2. I do apologize. Okay. So over here, we can put in 0.2, not minus 3, sorry, is equal to 4.5. Okay, we call it minus 4.5. Okay, so over here, we come up with a value. So stress A is equal to 0.2 divided by 1, then minus by minus 4.5 divided by 5. Okay, so this will become, so 4.7.9, so this is equal to 0.2 plus by 0.9. So now this is equal to what? 1.1. Right? So when this is the case, the structure is greater than what? Is greater than 1. So the structure will yield. Okay. So a very important thing to take note, based on this formula, the ultimate tensile and the ultimate compression, as you can see over here, I'm going to do a general one. This one. So if you look over here, right, the ultimate tensile and the ultimate compression, okay. So what we see down here, this you only quote the what? Magnitude, okay. If the ultimate tensile is equal to 1, you put in 1. And if the ultimate compression is equal to 5, you just put in 5. Okay. I know compression is usually is associated with a negative sign. Okay, but do not include the what? Negative sign. So just put in the magnitude 5. Where else stress A and stress B over here, both of them are what? Vectors. So you have to consider their magnitude plus what? Direction. Okay, so if it's minus, you have to include the minus. If it's plus, you have to include the plus. So that's the thing to watch for using Mohs criteria. Okay, any questions so far from anyone, please? Anyone? Okay, I don't hear anyone asking questions. So I'll go directly to we'll do an example. Okay, so example number 1. So all these examples that are given, okay, they should be, or any questions with Mohs criteria, you'll be able to identify, because they will tell you that you will have a ultimate tensile, which is equal to 10 times 10 to the power 3 psi. Then you have the ultimate compression. Okay, so they will say this is minus 30 times 10 to the power 3 psi. Okay, so like what I told you before, when we use Mohs criteria, when we have stress A over stress ultimate tensile minus by stress B over stress ultimate compression is equal to 1, right? All these value, the ultimate tensile and ultimate compression, we only need to care about the what? About the magnitude. We are not bothered about the what? The direction at all. Okay, right? So given that those are our physical or our mechanical properties of a structure, then we are given an element, okay, x, y, and then we have z. Okay, so I'm going to construct an element now. Okay, so this is our element. So in our element over here, if we look at our stresses acting on the element, so this will be equal to 2000 psi. In tensile, then we have in compression 15,000 psi, and then we have a shear, a positive shear configuration, and this is equal to 9,000 psi. So this is what is given. Okay, so we were the question asked, or this example want us to determine, okay, were the want us to determine will the material fail will the material not fail, will the material yield under the loading condition? And it's going to be based on the simplified Mohs criteria. So as we mentioned before, Mohs criteria works best for what? Brittle material, is for brittle material. So now in order to use Mohs criteria, right, we have to now identify what is our stress, a principal stress A, and we also have to identify what is our principal stress B. Okay, so we have to find stress A and stress B. Okay, and then we have to check if it's less than 1 or greater than 1. Okay, so from here it's like a typical Mohs circle question now. So we're going to label this now. So this is my point X, this is going to be my point Y on Mohs circle, and this surface is going to be my point Z. Remember, we're always dealing with 3D. Okay, so this will be ideal to apply the simplified Mohs circle because stress Z is equal to what? 0. So when that's the case, we know that we did this last week. This is known as a plane stress condition. Okay. So we have to construct. We still can. No doubt it's classified as plane stress condition. We can still construct Mohs circle. Okay. We can still construct Mohs circle. Right. So now we are going to go and construct our Mohs circle now. Okay. We're going to construct our Mohs circle that was given to us. So I'm going to change my paper view now to graph. So this is our normal stress. So minus 20, 16, 14, 12, 10, 8, 6, 4, 2, 0. I might need to squeeze it a bit more. Okay, so this is 2, 4, 6, right at the edge. Okay, so this is our normal stress. Then we have our shearing stress. Okay, so this is our shear stress. Oh, wrong intersection. So this is our shear stress, clockwise rotation of the element, anti-clockwise rotation. So minus 2, minus 4, minus 6, minus 8, minus 10, and I think I need more. This is a big circle. Or I'm just drawing too big. So this is minus 12, right? Then we will have 2, 4, 6, 8, 10, 12. Okay, so now we have to identify our points on Mohs circle. So this over here is, so our normal stress is 2000. So this is one of our line. So this is our stress X line. Then our stress Y line is at minus 15,000. So we have minus 15,000 over here. So this is our stress Y line. And we have our stress Z line, which is 0. And immediately we know where our Z point is. Okay, our Z point is exactly over here. So this is our Z.